The idea of today is to cover some foundational theorems that are related to simplex, and we will see that building step by step, and we'll see how simplex algorithm work. I have kept some details, so this session may become a bit engaging. If you feel that it is becoming difficult, you can come back to this video and watch again. I have tried to keep it as simple as possible. Okay, so yeah. So about me, I am Shubham Keshri, a PhD scholar in the Department of Management Sciences, IIT Kanpur. This is my LinkedIn profile. You can come and send me a connection request, and this is my email ID. You can contact me anytime you like. Okay. So acknowledgement. So this complete session is actually made from one course I did, which is done by my supervisor, Dr. Abhijit Khandra. The course was Operations Research for Management. And yeah, everything which I will cover in this lecture is directly or indirectly taken from that course. Objective of this session to understand the graphical method first. So we'll see how graphical method works. And I am pretty sure all of you know what we'll cover in graphical method. Then we'll move on to how to translate the concepts we have learned in graphical method to see how simplex work. Before going to simplex, we'll see some fundamental theorems. So I have written fundamental theorem, but there are other theorems as well, which will help us build the simplex algorithm. And then we'll examine, yeah, that is it. We'll examine the foundational principles of simplex algorithm. So this is the content of today's lecture. We will see as we proceed. Okay. So I hope my audio video is clear and my PPT is also visible. All right. Okay, so first of all, we will see one example of graphical method. So this is the problem: maximize 2x minus y such that x is, so there are three constraints and there are non-negativity restrictions. So what we'll do is we'll first draw the constraints and then determine the set of points that satisfy all the constraints. So it means we will try to find the feasible region. And then we will draw an isocost or isoprofit line. We will see what an isocost and isoprofit line is. So first of all, there are three constraints: x less than equals to 3, x minus y is less than equals to 1, and x minus 2y greater than equals to 0. Okay. So when you draw these three constraints, I have already drawn for the sake of time. I have already drawn it. So this will be the three constraints: constraint 1, constraint 2, and constraint 3. And this is the feasible region. I have marked it shaded. This shaded region is the feasible region. Okay. So we have the feasible region, the set of all points which satisfies the three constraints. Now let us see how we will draw the objective function. So you see, take any point in the feasible region. Suppose we are taking this point as 1, 1 by 4. Suppose this is the point in the feasible region we are taking, and we'll plug this into the objective function. Okay. So we'll see what the objective function becomes. So when we plug it here, it becomes, so since this is a feasible region, so it is a feasible point and we can get the objective function for this point. So it will become 2 minus 1 by 4, which is actually 7 by 4. So we have an equation: 2x minus y is equals to 7 by 4. You can plot this line, and this line will look something like this. It may not be to scale, but it will be something like this. This line, at this line, if you move in this line upwards or downwards, you will see that the objective function remains the same. What does it mean? It means that all the points in this line, which is also a feasible point, all the feasible points in this line have the same objective function value. I will repeat again. All the points in this line, all the feasible points in this line has the same objective function value. And this is why this line is known as isocost or isoprofit line, depending upon minimization or maximization. So this is a maximization problem. So we can say this is an isoprofit line. Now, if you take any point to the left of this line or the right of this line, you will know whether the objective function value is decreasing or increasing. So suppose we take a point at this end, and again we plug that value to the objective function value. You will observe that this side the objective function value is increasing and this side the objective function value is decreasing. Therefore, we will try to, so as this is a maximization problem, we will move this isocost or isoprofit line towards the direction in which the objective function value increases. So we will move this line in this direction. And you will observe that when this line moves in this direction, it exits the feasible region at this point. And this is the point at which the objective function value will be maximum. Okay, this point is 2, 1. Is that all right? So we observe 2, 1 is the optimal solution, which is a corner point of this feasible region. Is that all right? So we have observed that this isocost or isoprofit line exits the feasible region via a point, which is a corner point. And at that point, the objective function takes the maximum value. Okay? So we will come why I have highlighted this corner point. Okay? Again, I have another problem with the same constraints, but the objective function has changed. The objective function is x comma y. So again, the feasible region remains the same as the constraints are the same. We take again one point, and it is again 1 by 4. So you will get x minus 1 by 4, x minus y, which is 1 minus 1 by 4, which is 3 by 4. So you plot this line. When you plot this line, you will observe that it becomes like this. So this is the line you are getting. X minus y is equals to 3 by 4. Okay. Now again, you move it in the direction of improvement. So you will observe this side is the region where the objective function value will increase, and this side is the region where the objective function value decrease. And when you move it towards the direction of improvement, you will see that the objective function exits the feasible region touching this constraint. It will exit via this constraint. So it will become, it is actually parallel to that constraint. And when it exits, then all the points in this constraints are optimal. Okay. All the points in this objective function value has the same, all the points in this line has the same objective function value and are optimal points. But the observation is that two corner points, 1, 0 and 2, 1, these 2 points, which are corner points, are optimal. Okay, all points on the line segment connecting the points 1, 0 and 2, 1 are optimal. And this observation that a corner point is optimal holds true as long as the feasible region is bounded. So this I have written something which I have not proved, but it says that if the feasible region is bounded, a corner point will be optimal. Okay, so this is an observation we have made and we have not proved it yet. Is that all right? Okay. So what is the significance of corner point? The observation is LP's optimal solution is always at a corner point. The observation holds true as long as the feasible region is bounded. So we will see another example what happens when the feasible region is not bounded. Feasible region of a 2 variable LP is bounded. If bounded is known as a convex polygon. So what is a convex polygon? A polygon with internal angle less than equals to 180 degrees is known as a convex polygon. So it says that the feasible region of an LP, if bounded, it will become a convex polygon. Okay. So something like this hexagon can be a feasible region of an LP. Okay. Isocost and isoprofit line always passes through the corner point when leaving the feasible region for improvement. Comparing corner points allows for the determination of optimal solution. So this is very important. So you don't need to check for all the feasible regions, all the points in the feasible region to check for the maxima point. You can just go to the corner points, plug in the values of the objective function, and then you will pick the point with the maximum objective function value and state that that is the optimal solution for that problem. Okay. Then another example I have taken where there are 2 constraints and 1 objective function. So I have actually go ahead and drawn the constraint for sake of time. Now, if you see this feasible region is unbounded, you have 2 constraints, and this shaded portion is the feasible region. One end of the feasible region, there is unboundedness. You can go as high as possible in that direction. Now, we will do the same task again. We will pick a point. So suppose we are taking as 1, 1. And if you pick this point and plug it over here, so it will be 2x minus y. And if you put 1, 1, it will become 1. And we draw this line again. So it will look like this, something like this. It will look something like this. It may not be appropriate, but it will look something like this. Now, if you again do the same task, you will observe that this side is the portion where the objective function value increases. This isocost line has the direction of improvement in this direction. And this line exits the feasible region via this point. So it is exiting the feasible region via this point, and it is again a corner point, which is 3, 2. Okay. So this is one observation we made here. Here we notice that the feasible region is not bounded. The feasible region is not bounded, but we move in the direction of improvement, and the isocost line or isoprofit line leaves the feasible region via a corner point. Hence, it is optimal. Since the isocost or isoprofit line is leaving the feasible region via a corner point, then we can say for sure that that point is the optimal solution for that problem, although the feasible region of the problem is unbounded. Okay. Now again, the same constraints, but the objective function I have changed, which is now x plus y.
Hello.
So if you plot,
Hello.
yes.
Yeah, I have a doubt. So let's suppose we take a point between two. Go to the graph, right? Yeah, this graph. Like, let's suppose we take a point between 2, 3. X is
3.
between 2, 3, and let y be infinity. Y we can take it as infinity, right? Oh,
2,
sorry, sorry.
3. So you have already
Okay.
saying 3,
No, no,
right?
no. I get it. I'm wrong. Actually, I was assuming something else, so I'm wrong. Okay, you can go. I figured it out.
All right. So the feasible region is same in this problem. So I have drawn the same feasible region. Now the objective function is x plus y. So when you plot x plus y, it will be something like this. It will look like this. And this is the isocost or isoprofit line. And when you see, you will observe that this is the direction of improvement. And if you move this isocost line in this direction, you will see it moves like this. It moves parallel to this. And you will observe that it never leaves the feasible region. There are some points which will always remain feasible. In this case, you don't have a point which is optimal. So therefore, you can say that there is no optimal solution for this problem. The objective can increase and increase. You will not leave the feasible region in this case. Is that all right? Is that all right? Okay. So here, the movement towards the direction of improvement never ends, and we can improve the objective function value indefinite. That is, an optimal solution does not exist. This is the technical term. Or in non-technical terms, you can say that the solution is unbounded. In general, so this is important. In general, if the feasible region is unbounded, so we can have feasible region which is unbounded, but we can have optimal solution as well as no optimal solutions. So it says that if the feasible region is unbounded, an optimal solution may or may not exist. You may have an optimal solution, you may not have an optimal solution. However, if it exists, if there is a feasible optimal solution, then a corner point is optimal. So this, we are coming back again and again the thing about corner point, and we will see that the corner point being optimal is not only true for two-dimensional LP, it is also true for higher dimensional LP. And we will also see what does a corner point for higher dimensional LP represent, or how do we think about it, how do we go about it, what is the name of a point which is a corner point for a higher dimensional LP. We will see those things. Just for sake of completeness, I have a problem which is infeasible. So if you plot the constraints, you will see that one is in this direction, one is in this direction, and one in this direction. So there is no feasible region in this problem. Therefore, the problem is infeasible. The LP doesn't have a feasible solution. Is that all right?
Yes.
Okay. So I hope it is all right. Now, what I am doing is I am writing an algorithm. So this is an algorithm to solve graphical method or to solve linear programming problem with two variables. So what we should do is we should construct the constraints and determine the feasible region. If no feasible region exists, then declare the problem to be infeasible and you stop. You don't need to go further. If the feasible region is bounded, so you see, we had two things: if the feasible region is bounded or if the feasible region is unbounded. So we have cases for both. If the feasible region is bounded, compare all corner points in terms of the objective function value. Declare the best corner point optimal and stop. So if the feasible region is bounded, you check each of the corner points and see which has the best objective function value. And then you declare that solution as the optimal solution and you stop. If the feasible region is unbounded, then you have two cases. If the optimal solution exists, so if the optimal solution exists, compare the corner points, whichever has the best corner point, declare it to be optimal. If the optimal solution does not exist, declare that and stop. So we have an algorithm which checks one by one for all the cases, and you will always have one or the other. You will conclude with one or the other. A infeasible solution, an optimal solution, or an unbounded solution. Okay. So these are the steps of graphical. Note that in point 3 and 4a, point 3 and 4a, it is possible to identify two corner points as optimal, or just a minute, two corner points as optimal. Then all the points in the line segment connecting these 2 points are optimal. Okay, so if you have multiple optimal solutions, what you will observe is there are 2 corner points in your graph having the same objective function value. In that case, you know that the line segment connecting those 2 points will also have the same objective function value, and there are multiple optimal solutions for this problem. Yes, so someone is raising his or her hand. You can ask questions.
Yeah, Shubham, how do we know in the 4-2 after checking the 3 corners whether we have found a solution or not?
Right.
Because the, yeah.
So this is a good question, which I have not written here. So you can do it algebraically also. So what I have shown you here is graphically. You are plotting the isocost or isoprofit line and you are moving it. This is not an efficient way to do because your graph can be, or your feasible region can be too complex. And you may not draw the graphical, the graph uh, to scale. So what may happen is you may get a graph which is not accurately depicting the feasible region. So there are algebraic methods where you take the objective function as big M and then you calculate. There are methods which I'm not going here. So I'll give you resources if you want to check unboundedness of a solution when there is such case. Okay, so I'm not going into that details here. Is that all right? Okay, I suppose it is all right. So we have discussed a two-dimensional problem. Now we have to think about how to translate this idea. So we have an idea of how to solve a two-dimensional problem. Now we have to think about ideas of translating this solution method to a higher dimensional problem when you have 3 variables, 4 variables, n variables. So the questions we should think about is, how are we sure? So first question is, how are we sure that a corner point of a feasible region of an LP is optimal? So this is not about higher dimension. We have made an observation which states that always a corner point is optimal. But how can we be sure that the corner point of a feasible region of an LP is optimal? So we have theorems for this, which states that the corner point of a feasible region, if it is bounded, it is optimal. We will see. I have kept those theorems over here. So this is the first question we should think about. Second question is, what does a corner point in higher dimension mean? Oh, I have not written here. Should be mean. What does a corner point in higher dimension mean? Okay. And the last thing is to think about is how to identify these corner points equivalent of this corner point in higher dimension. So in 2 dimensions, we can easily see which are the corner points, or we can solve it simultaneously and get all the corner points. But how do we identify these corner points when we are going in higher dimensions? Okay, so this is the few things we should think about when we are moving towards higher dimensional LPs. Okay. Now, what we will do is we will cover few concepts. It may seem that they are detached or separate concepts, but all will come together. Just bear with me. So this is one form in which you can write any LP, which is known as the canonical form. In this form, the objective is of maximization type. The constraints are of less than equals to type, and the variables are greater than equals to 0 type. Okay. So this is a form which any LP can be converted to. So if you don't know how to convert an LP in canonical form, you can go and read books. But take my words, any LP can be converted to canonical form. And this is what a canonical form is: a maximization type objective. The constraints are less than equals to type, and the variables are greater than equals to type. Okay. So we will use canonical form of LP going
Hello.
forward. So this I have just,
Yeah.
yes.
Hello. I have one doubt. So in canonical form, always the objective should be maximized and then subject to less than equal to, or
Yes,
it can
yes.
be like mean and greater than equal to as well. Is that also possible?
I suppose it is possible. I may be incorrect, but as far as I have read this type. I don't know. It may be correct. It may not be correct. I will not be able to comment right now. Is that all
Okay.
right?
Okay. Okay. Okay.
Okay. So So feasible region of an LP. What is a feasible region of LP? In linear programming, the feasible region refers to the set of all feasible solutions that satisfies the constraint of the problem. We know this. The feasible region is determined by the intersection of the constraints inequality. So we see which is the intersection region of the constraints. Each point within the feasible region represents a feasible solution. So these are all the points we already know, but this is here for a reason, because we will proceed forward and we will see a convex set. So it says that the feasible region of an LP is a convex set. Okay. So we will first see what a convex set is, and we are stating that a feasible region of an LP is a convex set. So what is a convex set? A set is convex if for any 2 points within the set, the line segment connecting them lies entirely within the set. So suppose I have a square, and the convex set for this square is all the points inside this square and the corner of this square. So you see, take any 2 points inside this feasible region. So suppose inside this convex set, these 2 points you are taking. And if you connect a line between these 2 points, you will observe that all the points in this line, which lie in this line segment, is inside this convex set. If you take a circle, then also you will see that this is a convex set. You take any 2 points in this set, if the line segment connecting these 2 points, all the point in those line segment will be feasible. So these are examples of convex set. For example, this diagram, a diagram of an arrow. This is not a convex set. Why? Because you can easily observe that if you take 2 points in this set, and if you connect these 2 points, there are points in this line segment which is outside this set. Okay, so this is not a convex set. So this is the definition of convex set. Okay, in the context of linear programming, it means that any convex combination of, okay, I will come to this. So this is the definition of convex set, and it says that the feasible region of an LP is a convex set, but the converse is not true. What it means is all convex sets are not feasible region of LP. You see, this is also a convex set, this is also a convex set, but this cannot be a feasible region of LP. Why? Because this is nonlinear. So the converse is not true. We can go in one direction. We can say that the feasible region of an LP is a convex set, but all convex sets are not LP's feasible region. So what is the second point which I skipped? It says that it means it is some portion. So when I said,
so I
yes.
wanted to add that when you are saying convex set, the convex set which don't have 100 more than 180 degree between two in any corner, right?
So we are not talking about convex polygon. Earlier we were talking about convex polygon. This is a convex set. Is that all right? Okay. So when I'm saying take 2 points and connect the 2 points via line segment, doing this is known as a convex combination. So what does it mean? If you take, suppose, point Y and point Z, and you want to get a point in between these 2 points, so what you do is you multiply one point by lambda and the other point by 1 minus lambda, where lambda lies in, sorry, not this, when lambda lies between 0, 1. So when you do this, or you can just take lambda lies between 0, 1. So when you do this, you can get any point in between Y and Z. You see, you can vary lambda from 0 to 1, and you can come from this end to this end. Okay. So this is what is meant by convex combination. So X is represented as a convex combination of the points Y and Z. So it says that in the context of linear programming, it means that any convex combination of feasible solution is also a feasible solution. So I will repeat again. It says that in linear programming, any convex combination of feasible solutions. So suppose this is the feasible region of a LP. Any convex combination of these two feasible solutions will also be feasible. It means the same thing. I'm just talking about in context of mathematics. So that's why the terminology convex combination. Is that all right? Okay.
Hello.
So yes.
Can you explain why converse is not true?
So I gave you an example.
Yes.
I gave you an example of a circle, right? So suppose this is a circle. This is a convex set. This is correct, right? This is a convex set. Are you convinced about that? That a circle is a
Yes.
convex, but it cannot be a feasible region of an LP. The constraints will be non-linear, so it doesn't represent the constraint of a linear programming problem. Is it all right?
But it can be possible for non-linear constraint.
So
If we have
LP, when I'm saying LP, it means linear programming, right? I'm not saying in non-linear programming. I'm not talking about non-linear programming.
Okay.
I'm talking about not feasible region of an LP. I'm not talking about non-linear programming. Is it all right?
Yes.
Okay. I
Yes.
guess it's not clear, but think about it. It will become clear. Okay. So I can skip this part because this is not important. So for the time being, I'm skipping this portion. Okay. We can come to that point, but we will skip for now. Okay. Now we have talked about a convex set. Now there are three important set of points we will discuss: interior points, boundary points, and extreme points. So what is an interior point? A point X is an interior point of a convex set S if there exists a neighborhood in X that is entirely contained within S. So what does it mean? You see, just a minute. So draw a convex set. So suppose I'm drawing a convex set, a circle. Okay. So what are interior points? Interior points are those points in this convex set S if there exists a neighborhood of X that is entirely contained within this set. So suppose take this point in this convex set. You create a neighborhood. So in 2 dimension, a neighborhood is actually a circle. Okay. Now you observe all the points in the neighborhood is actually within this set. So this point is an interior point. Interior point. You take a point over here and you create a neighborhood. So when you create a neighborhood, you see all the points in this neighborhood is not contained within the set S. Therefore, this is not an interior point. Is that all right? So interior point just means if that point belongs to that set, the neighborhood around that point will also belong to that set. Is it all right? So for example, if I take a triangle, sorry for the bad drawing. So if I take a triangle, so all the points inside this triangle are interior points, but no point in this vertex will be an interior point, because if you draw a neighborhood around that point, all the points in that neighborhood will not lie in the convex set. Therefore, this is not an interior point. Am I making sense, or it is becoming too complex?
Making sense.
Okay. So what is a boundary point? A point which is not an interior point is a boundary point. So for example, this is a boundary point. This is a boundary point. This is also a boundary point. Is that all right? So if a point is not an interior point, then it is a boundary point. Now there is a very important set of points, or a terminology you can say, which is known as extreme point. So what is an extreme point? Then we know what is an interior point. We know what is a boundary point. What is an extreme point? A boundary point is an extreme point. So extreme point is actually a subset of boundary points. A boundary point is an extreme point of a convex set S if. So I will not read further. I will just explain to you first and then it will make sense. Okay. So extreme point. So suppose you take this point. Okay. What you do is, if you can create a line segment connecting two other points, you can create a line segment connecting two other points, and this point is in that line, then it is not an extreme point. So what it means is, suppose you're talking about this point. Now, if you can take 2 points and create a line between these 2 points, now this point is actually in this line, therefore it is not an extreme point. Extreme point are only those points if it does not lie on the line segment connecting any 2 points in the set. So for example, this is an extreme point. So you cannot take any 2 points belonging to that set and create a line such that that point will be in that line. So this point is an extreme point. This point is also an extreme point. This point is also an extreme point. And any point in this circle is also an extreme point. You cannot take 2 points belonging to the convex set, connect those 2 points. This point will not lie in that line. So interior point, boundary point, and extreme point. So you see it is
So,
very
sir,
similar to corner points. Just I will come back. I will come back just a minute. So it is very similar to corner points in 2 dimension, right? So corner points and extreme points are actually the same thing in 2 dimension. See the similarity. So an extreme point is that point where you cannot find 2 points in the same set and connect those 2 points, and that point will not lie in that line segment. So yes, Gopal is asking some question.
For interior point, is there any specific distance from that point
No,
for
no.
the
So
neighborhoods?
when you define neighborhood, it is actually a unbounded neighborhood. It is open set. The size of the neighborhood is not fixed. It is actually a small neighborhood.
Okay, because sometimes if we have some points near the boundary, and if you take neighborhood very far from that point, then it become a means that
No,
point is not an interior point, right? If you
I
take the
understand
neighborhood
your
very
doubt.
close to that point, then it is an interior point.
Right. So you see the definition. It says that if there exists a neighborhood, so why will you create a big neighborhood? You create a small neighborhood. You can create a neighborhood, right?
That's why I'm asking. Is there any specific measurement of how far the
No,
neighborhood should be?
it
Something
says
like
that. So suppose there is a line, and it is in 1 dimension, right? It is in 1 dimension. Now, if you take the neighborhood of 1 point, it is actually a line segment. The neighborhood in a 1 dimensional line is a line segment. Now, suppose the line is from 0 to 1, and you are talking about the point 0.99999, and you want to see if this point is an interior point or not. So what you do is take a neighborhood. You add 0.000001 and subtract 0.000001. So you could create a neighborhood which lies between this set, in this set, right? It doesn't matter what the size of neighborhood is. It just says, is it possible to create a neighborhood or not? So I can create a neighborhood which lies within this set. Is that all right?
Yes, fine.
Okay.
So
I hope, yes.
Hello.
Yes.
So extreme points is also considered in a convex set or not?
Yes, all the points belongs to the set. All the points should belong to the set.
Extreme point will consider as a convex set or not? I mean, there is a definition of convex set that there exists a point in which there exists 2 points in which we plot a line, then that point comes under
Okay,
that
good,
set S.
good question. Good question. So suppose you are talking about a boundary point. So you take this point and this point, and now you are saying, how can a point lie between these two sets? So you see, when we are talking about convex set, x is equals to lambda y plus 1 minus lambda z. So you take, in this case, when defining convex set, you take this point as lambda is equals to 0. Or you can see like this. So when you take lambda is equals to 0, it will come at one end. But so over here, lambda belongs to the closed set 0, 1. But when I'm talking about interior point, then that lambda belongs to open interval 0, 1. So it means the convex set, the boundary points are set of belongs to the convex set. Yes, Shiva.
Yes, sir.
Yes, you had some doubt, right? Okay. So I was clear, right, Manoj?
Yes, sir.
Okay. And you can call
Yes,
me
sir.
Shubham. Don't call me sir. Yeah. Go ahead.
Yeah, I just asked the question. Interior point question.
Okay. Manoj, you have any question?
Yes, sir. In the case of triangle, you said boundary point can be extreme point also, right?
Yes.
I mean, boundary point is a subset of extreme point in case of triangle.
No.
But in
Extreme point is a subset of boundary point.
okay. And in case of circle, you have written extreme point and boundary point also. So, in the case of circle, can a boundary point also be a extreme point, or what is the difference?
All boundary points are extreme point. In a circle, all boundary points are extreme points.
Okay, got it, sir. Thank you.
Okay. So this is Yash.
Yeah, I have one question that if there is a point which is extreme point, is it also a corner point?
So you see, we are talking about a convex set. So inside, so in the definition of convex set, we don't have a corner point definition. Is that all right?
Mhm.
Okay, so I will proceed further. Okay, so these are few things I have written. It can be shown that feasible region of an LP in canonical form has at least one extreme point. So this is very important. You see what it says. So if you have a LP and you have written it in the canonical form, then its feasible region will have at least one extreme point. Okay, so it will always have one extreme point. Also, the number of extreme points are finite. Why is this important? It means that you will have a corner point to check. So the feasible region of LP will always have at least one extreme point. The second thing is extreme point plays a same role in simplex algorithm that the corner point was playing in graphical method. So that is what I want. I will relate corner point and extreme point. They are the same thing. That is what I wanted to relate. So in higher dimension, we will not call it as corner point. We will call it as extreme point. Is that all right? There are some hands raised. If you don't have doubt, you can please put down your hands. Is that all right? Okay. So representation theorem of polytope. So I have not talked about what a polytope is. So let me go back and see. So I will go through these definitions, but this is not very important right now. Okay. So for the time being, you can assume that in higher dimension, if the feasible region is bounded, then we will call it as polytope. Okay. For the time being, just assume this. Again, I will repeat, in higher dimension, if you're not in higher dimension, in any dimension, if the feasible region of an LP is bounded, then it is known as a polytope. So that is why I have written a representation theorem for polytope. So what it says, I will just tell you in the context of two dimensions. So suppose this is the feasible region. Suppose this is the feasible region of an LP. I will not go into too much detail. I will just give you ideas. Okay. So this representation theorem for a polytope, it says that. So first of all, since it is a polytope, then it means that the feasible region is bounded. There is no unboundedness. Okay. So, sorry. Okay. Now what this representation theorem says is that take any point in the feasible region, no matter if it is inside the feasible region or it is in the constraint or a corner point, it doesn't matter. Take any point in the feasible region. Now you can represent that point. So suppose X is that point. So you can represent X in terms of the corner points. So this is Y1, this is Y2, this is Y3, this is Y4, Y4. So what you can do is you can represent X in terms of corner points. Over here corner points, but in general it is extreme points. So lambda 1 Y1 plus lambda 2 Y2 plus lambda 3 Y3 plus lambda 4 Y4, where lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 equals to 1, and lambda I is greater than equals to 0 for all I in 1, 2, 3, and 4. Okay. So this is what it means. X is equals to lambda 1 y1 plus lambda 2 y2 plus lambda 3 y3 plus lambda 4 y4. Because there are 4 points, that's why I have written 4 points over here. And the condition is lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 is equals to 1, and all lambda i's are greater than equals to 0. So this is what representation theorem for a polytope says. Any point in the feasible region, you can represent it as a convex combination of the extreme points, or in other words, so I will repeat again. Any point in the feasible region of an LP, you can represent it as a convex combination of the extreme points of that LP. Okay, so this is a convex combination because lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 is equals to 1. So the sum is 1, and all lambda i's are greater than equals to 0. So this is a representation theorem. You can go further. You see, when X can be represented as this. So the set of feasible region you can write like this. So the set of feasible region, that is all X's, can have this form. So you can have a set lambda 1. So I will write it as, just a minute. what you can do is you can write like this: X belongs to the set summation of lambda I yi such that lambda I summation is equals to 1 and lambda I belongs to, sorry, not belongs to, it is, it can, you can write belongs to 0, 1. Okay. Or you can just say lambda I greater than equals to 2, means the same thing. Okay. So this set, you see, this is a set. It can take any point. You vary lambda, you can vary lambda between 0 and 1. You can vary all these lambdas and you will get a set of all points inside the feasible region. So you can write the set of feasible region either in this way, or the constraints you can write ax less than equals to b, where x is a vector and b is a vector and e is a matrix. So you can write the set of feasible region either in by the set of constraints, or you can write the feasible region of an LP via this set. Okay, so these two sets are similar, and this, by the way, this is all right, right? I will introduce one more terminology. This is all right, right? Okay, so one terminology which is not very important right now, but for the sake of completeness, this is known as convex hull. If you don't want to remember it, you can forget about it because I'll not use any further. So the set of all the points using the corner extreme points is known as the convex hull of those points. You can just forget about it. I just mentioned it over here. The thing to take from here is any point in the feasible region. You see, the feasible region is actually continuous. The feasible region of an LP is continuous. There can be millions and uncountable number of points, right? But the beauty of representation theorem is that you can represent it using the corner points. Although you can vary, just a minute, although you can vary lambda and get all points, but you can represent it in using finite number of points. Why finite? Because I have already said the number of extreme points is finite. You cannot have an infinite number of extreme points. So you are just converting the feasible region in a way that you can represent it with finite number of points. Although there are lambda i's, but you can represent it using finite number of points. So there was some question you can ask now.
Yeah, so I just want to ask you one question. So one thing you mentioned about lambda yi, right? So can we consider all yi's as extreme points?
So you have to write it in all the extreme points. If there are n number of extreme points,
So
this
n
convex combination will take n number of points.
Okay. And other thing you mentioned is feasible region. Okay, so basically inside a region there will be infinite points, right? Like how can we say it's a finite point? Well,
So
region is bounded, we know, but there can be infinite points inside the region.
Infinite point inside the region, that is true. But what I am saying is you are representing that infinite feasible region using finite set of points. These extreme points are finite. It will be n number of points. Although you can vary lambda i's and get all the points, all the infinite number of points, but you are representing it using finite number of points.
Okay, thank you very much.
Okay, so this is what it is. But now it has a consequence. What is the consequence? I will not go into the detail of the consequence because I'm seeing I don't have a lot of time. But there is a consequence of this theorem. What is the consequence of this theorem? You see, since you are representing each point using lambda I yi, so you see, take for example this point, x is equals to lambda 1 y1 plus lambda 2 y2, and so on for lambda 4 y4. So there are 4 number of corner points. Now you see, suppose this or this or this or this. Suppose in this 4 of them, suppose one is so one is taking 4 value, one is 5, one is 6, one is 7. Okay, so these are coming out to be 4, 5, 6, and 7. Now you see, one of those, if this is 7, you can just put lambda 4 is equals to 1 and all other lambda 1, lambda 2, lambda 3 as 0. So now you see you can obtain the maximum value. You can obtain 4, 5, 6, 7, and any value in between 4, 5, 6, and 7. But if you put lambda 4 as 1, you will get the maximum value. Is that all right? Is that correct? Because lambda i's vary between 0 and 1. So what you will do is whichever of this is highest, you put that as 1, that lambda I to be 1 and all other to be 0, and you will get the highest value. So not over here. It is actually, so I have just missed one thing. So this is actually, so what I'm saying is, this is how I just repeat again. So what I missed is, so this is how you are representing a point X. The objective function value maximum is actually C times X, right? So you will have lambda1 C1 Y1 plus lambda2 C2 Y2 and so on. So that will take, this will take 4, this will take 5, that will take 6 and so on. Now it is correct. So you will plug one of them, those lambdas to be 1 and plug others as 0. Now you see you have obtained the highest objective function value. You obtain the highest objective function value. So what is the consequence? You can use these extreme points, just the extreme points, to get the maximum value. It means that extreme points will be optimal. No other point inside this region will be optimal. Only one of the extreme points will be optimal given the feasible region is bounded. So the consequence of this theorem says that always a corner point will be optimal. Always an extreme point will be optimal. So if you go back over here, we were talking about 3 questions. How are we sure that a corner point of a feasible region of an LP is optimal? This theorem says that if there is a corner point and the feasible region is bounded, that corner point will, one of those corner points will be optimal, or like an extreme point is optimal. Is that all right? Is it clear?
Shubham,
Yes,
one
yes,
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 it's clear.
Sure.
It's
One
yes,
question. So basically, we
yes,
started with the premise saying that we knew the number of extreme points in that polygon, and because of
yes,
that, we added so many number of variables, right? And again,
yes.
we are trying to make it all the other things as zero and trying to achieve find out the maximum values there for each corner extreme point.
So I did not get your question. I will repeat once more. If you don't understand, please tell me. You see, what we are saying is we can represent any feasible point as summation of lambda I yi. I is equals to 1 to n. Now, what is the objective function? Objective function is written as C times x bar, right? So this is also x bar. Now C times x bar. So what you will get is lambda1 C1 Y1 plus lambda2 C2 Y2 plus dot 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 lambda n Cn yn. So your objective function becomes, so takes in terms of y, changes from x to y. Now you have a problem in y, not in x. And the variables are lambda1, lambda2, lambda. So the variables will be summation of the variables. The constraints will be lambda I, summation of lambda I is 1 and lambda I is greater than equals to 0. Now you are changing lambda i's such that you get a maximum value. If any of these takes a maximum value, you plug that lambda n as 1 and put others as 0. If two of them are taking the same value, then you can see 2 points are optimal, lambda I and lambda j. Then there are multiple optimal solutions, and any point in between those 2 points, lambda I and lambda j, will be optimal. So what was your question? Did I answer your question?
No, my question was, so basically, initially you have the number, you have to know the number of extreme points to frame that equation, right? To identify the number of points and lambdas.
Right.
And
Yes.
so we get that number of extreme points by looking at the equation, and we identify, we calculate the value of those extreme points later by substituting all the lambdas to be 0 and one of the lambdas to be 1. Is it?
Yes. Yes, you are correct. So you see, this is a very inefficient approach. There can be millions and millions of corner points. You just cannot go and check for each of the, not corner points, the extreme points. You cannot just go to each of the extreme points and see if it is optimal or not, right? Or plug in these values and then put one as the extreme points. So we are building to that algorithm. But here are the ideas. Is that all right?
Right. Understood.
Right. Okay. So that was about representation theorem of a polytope. Now, this is a generalized representation theorem. So I will not go into the detail of generalized representation theorem. It is just saying the same thing for an unbounded region, unbounded feasible region. I will skip this for sake of time. Okay. So, but the conclusion remains the same. if LP with unbounded region has an optimal solution, if it has an optimal solution, then an extreme point is optimal. So the thing is clear. Always an extreme point will be optimal. If optimal solution exists. If the optimal solution does not exist, then we cannot say what is the optimal solution. It is unbounded feasible region and the objective function value is unbounded. If the optimal solution exists, it will always be at a corner point. Is that all right? Okay, I suppose it is all right. So you see, we have come from one direction and talked about extreme points. Now the thing is, how will Simplex identify a corner point? So what have we built? The theory till now is we know corner points are optimal. Now we went on to higher dimension and we said, okay, corner points and extreme points are the same thing, and extreme points are optimal. Now what we will build
Shubham, we are not able to hear you. There's a lot of noise.
Yeah.
Not-
Hello.
We're not able to hear you.
We are not able to hear you. Like it's no noise coming.
Is it better now?
Yeah. Now
Is
it's
it better now?
Yeah.
Okay.
Yeah, can you start
Okay. Thank you for.
from 2 minutes back, 2-3 minutes back? Can you start from this slide
Yes,
again?
yes. I will start. I will start. Just give me some time. I don't think I'll be able to complete by 7:30 though. So just bear with me. Okay. So what I was saying is LP in standard form. So LP in standard form states that all the constraints will be of equality type. And since we have discussed canonical form, so we will say that we have any LP, we will first convert it into canonical form, and then we will come to standard form. So initially, LP in canonical form will be something like this: ax less than equals to b bar. Now you add slack or surplus variable, whatever it is, and it will become ax is equals to, so this x and this x are different, ax is equals to b. Why this is different? Because there are some variables added, so it will have more variables. So I will give you an example to make you understand. Okay, so for example, I have 2x plus 3y less than equals to 4. So to convert this constraint into standard form, you add a slack variable, so it will be 2x plus 3y plus s1 is equals to 4. So this is how you convert each of the constraints in equality type, and then you will come up to a standard form. So why are we interested in standard form? You see, we have a set of equations, ax equals to b, and now we can use the theory of linear equations and then do something here. That is why we are interested in standard form. I will repeat again. We are interested in standard.
Shubham,
Yes.
there's a lot of
Yes.
background noise coming from your end. Can you just check once?
Just a give. Just give me. Okay. Better? Is that better?
Yeah, can you? But still, there is some background noise.
Yeah, there is still some background noise.
I don't know. I don't have some noise here. Is it now better?
Yeah, it is better now.
Okay. Thank you. So yeah. So I was there. What I'm saying, why are we interested in standard form? This is because we want to use some theory from system of linear equations. That is why we are converting our LP in standard form. Okay. So system of equations. A system of equations can be written as a matrix multiplication of A times a vector X, which is equals to a vector B. Okay. Now you see, A is a matrix where we can write A11, A12, and so on is AMN. Now you see, you can, instead of writing like this, you can write it in a different way. How you can write? You can write it like this: x1 times a1 plus x2 times a2 and xn times an is equals to b. Is it clear? What we are doing is, from matrix notation, we are converting it into a variable times a vector. So this x1 is multiplied by the first column, x2 is multiplied by the second column, and so on and so forth. So this is another way you can write the same equation. It is just a different way of writing. So a1 bar, a2 bar, and an bar are column vectors of the matrix A. Is that all right? Okay, I suppose it is all right. Now, what is a basic solution? So you see, we have written the constraints of an LP in this form: a1 x1 x1 a1 bar plus x2 a2 bar, and so on and so forth. So this is the way we have written the constraints of an LP. Now, what is a basic solution? You have this set of equations, you solve this. So a solution of this is a basic solution if the column vectors of A corresponding to non-zero component of x bar are linearly independent. So there are many terminologies here, but just understand like this. You are solving these equations. What are you solving for? You are solving for x1, x2, and xn. You are solving for x1, x2, xn, and so on for xn. Now, when you have solved this equation, you have a solution. You take those column vectors which have a non non-zero component, that is either positive or negative. So x1 can take value anything between any value. It can be positive, it can be negative. We are talking about system of linear equations. We are not talking about LPs. So x1 can take negative values, it can take 0, it can take positive values, it can take any value. Okay, take those column vectors where xi is non-zero. Okay, non-zero component. So suppose a1 bar, a2 bar, and a5 bar are those components of this system of equations which have x1, x2, and x5 as non-zero. Now, if these vectors are linearly independent, so this is something which is coming from matrix. If this is linearly independent, then this solution x1, x2, x5, and all other as 0 is known as a basic solution. Okay. So what will that solution look like? It will be like x1 comma 0, no, x1 comma x2 comma 0 comma 0 comma x5 comma 0 and 0 and so on. So these three components are non-zero and all others are 0. So this solution is known as a basic solution. Okay, is it all right? Is that all right? Now, why are we talking about this new concept here? We already know an extreme point, we already know corner point, we already know those are optimal. We are coming to these definitions because Simplex uses the idea of system of linear equations to solve an LP. And in system of linear equations, these are the terminologies used. Basic solutions, not basic feasible solution, basic solutions are used. Therefore, we will try to relate extreme point with these concepts. So what have we done till now? We knew corner points are optimal. We saw that corner points and extreme points are the same thing. Now what we are doing is we are trying to build one more theory about basic solutions and basic feasible solution, and we will say at last that extreme point and basic feasible solution are the same thing. Okay, so this is what we are doing. We know what is a corner point, we know what is extreme point, we know extreme points are optimal. Now from this theory we are coming, we know what is a basic solution, we will define what a basic feasible solution is, and we will say basic feasible solution and extreme points are the same thing. When we do that, then Simplex can use the ideas of basic solution and basic feasible solution using the theories of system of linear equations to solve an LP. Is that all right, or should I repeat? Is that all right, or should I repeat? Okay, so we'll talk about basic feasible solution right now. So we know what a basic solution is. We will solve this. We will solve this system of linear equations. We will take the non-zero component of, we will take the columns with non-zero component of the solution. If these vectors are linearly independent, then it is a basic solution. Now, what is a basic feasible solution? If these non-zero components are actually positive, is it positive or no? if it is positive, if these non-zero components are positive, then it is known as a basic feasible solution. Okay, just that restriction. Just a minute. So you have a basic solution. You can easily check if it is a basic feasible solution or not by seeing the non-zero component. If those are positive, then it is a basic feasible solution. Yes, Nikhilesh.
Shubham, here linearly independent columns, how we can check or how what that signifies?
So I will not talk about linearly independent. In other way, you can say if you solve this equation and you get a unique solution, if you solve this equation and if you get a unique solution, then it actually means that these columns are linearly independent. So these are different theories I'm talking about. I know there are a lot of theories, but this is how you will know that these columns are linearly independent. By solving this equation, if you get unique solution, no multiple solutions, no trivial solution, unique solution, then it is linearly independent. Okay.
Okay, thank you.
Okay, so we know what is a basic feasible solution. Now, what this fundamental theorem of LP says, the fundamental theorem of LP says extreme points and basic feasible solution are the same thing. Just that. Now, what Simplex has to do? It has to find basic feasible solution. If it finds basic feasible solution and checks all basic feasible solution, therefore it can find the best basic feasible solution and can define that basic feasible solution to be optimal. Okay. It is actually trying to find extreme points, but in the theory of system of linear equations. So what is the task of Simplex now? The task of Simplex is to find different basic feasible solutions and check what is the objective function value in those basic feasible solutions. I will not say the task of Simplex, I will say the task of an algorithm which is trying to solve an LP. So what is the task of that algorithm which is trying to solve LP? The task of that algorithm should be to check all the basic feasible solutions, check the objective function value at those basic feasible solution, whichever has the highest objective function value, declare that to be optimal. You see, the task has become so simple. It doesn't have to check all feasible solutions because those are infinite number of solutions. It just have to check all the basic feasible solutions. Okay, so this is the key, basic feasible solutions. So I will take one example of two variable LP and I will show how to find basic feasible solutions of that LP. So this is a maximization LP. These are the two constraints and this is in canonical form. You see, less than equals to type, greater than equals to type, maximization type. Okay. Now I have converted it into standard form. I have added slack variables. Instead of S, I have written x3, x4, doesn't matter. Okay, so this I have written as 0x3 plus 0x4. In constraint 1, x3 has a multiplier of 1 and x4 has a multiplier of 0, and this inequality becomes equality. So this is the standard form. Now what we have to do? You see, there are two equations. So from these two equations, we will pick two variables. Why? Because if you have so this is coming from the theory of linear algebra matrices. So if you have two equations, you can have at most two linearly independent columns or over here columns. Okay, so you can have at most two linearly independent columns. Therefore, we will pick two variables at a time. So what we will do is we will say x1 and x2, and we will take that column. What is the column for x1? The column for x1 is 5 and 10. So the column of x1 is 5 and 10. And the column of x2 is 20 and 15. 20 and 15. And we will put all these as 0. So x3 and x4 are 0. Why are we putting those as 0? You see, over here if you come back, we said take the non-zero variables, take their columns. It means other variables are taking 0 value. Therefore, in these two equations, I am setting x3 and x4 as 0. And we are solving for x2 and x1 and x2. So we are solving for x1 and x2. When you solve, you get this solution. Is it a basic solution? Yes. because we have a unique solution. This is a unique solution. You don't have infinite solution. This is a unique solution. In fact, all solutions are unique. Therefore, this is a basic solution. Now, is it a basic feasible solution? You see, whichever are non-zero, they are positive over here. So this is a basic feasible solution. Now, you set x1 and x4 as 0, and you take x1 and x3. For x1 and x3, you solve and you get a unique solution. This is a basic solution, yes, because it is a unique solution. Is it a basic feasible solution? Yes, because the non-zero components are positive. Again, you take two variables, set the other as 0, you get a solution. Is it a basic solution? Yes, because it is a unique solution. And is it a basic feasible solution? No, because one of them is negative. So in this way, you can identify what are we doing. We have an LP. We have an LP. We are identifying all basic solution of this LP. When we are identifying all basic solution of this LP, we are also identifying all basic feasible solution of this LP. So over here, there are 6 basic solution of this LP, and there are only 4 basic feasible solution of this LP. Now, for these 4 solutions, you just obtain the objective function value. So check what is the objective function value for this solution, check what is the objective function value for this solution, check for this and check for this. Whichever has the highest is the optimal solution. So we have a crude algorithm now. We actually have a crude algorithm. What we can do, take any LP, convert it into standard form via canonical form, check for all possible choices of these variables. Okay, how many choices you have? There are n variables and there are m rows. So over here, there are n represents the number of variables, which is 4, and m represents the number of constraints, which is 2. So you have 4 choose 2 number of choices to make. So over here, 4 choose 2 is actually 6. So you take 2 variables, x1, x2 from the set of 4, x1 and x3 from the set of 4, x1 and x4 from the set of 4. There are 6 choices. For all these choices, solve the set of equations. Identify if it is a basic solution, and then identify if it is a basic feasible solution. Now, when you know all the basic feasible solution, you just obtain the objective function value for all the basic feasible solution. When you do that, then you will be able to obtain the optimal. So I will repeat again. I know I have talked a lot. So the idea is, if you have an LP, you know there can be n choose m. These many numbers of choices you can make for basic variables. What is basic variable? Over here, from 4 variables, you are choosing 2. So you can make only 2 variables as non-zero. So you are first saying x1 and x2 are basic variables. So x1 and x2 are basic variables. Then you are saying x1 and x3 are basic variables. So you can make n choose m possible choices of basic variables. Solve this equation, you will get basic solutions. Then you identify basic feasible solution and then compare the objective function value. In doing so, you will get one basic feasible solution which is having the highest objective function value. Am I making sense, or have I gone on top of your head? Please speak up. So I have given, yeah, Shivalli.
Yeah, sure.
Yes, you can ask questions.
Understood. Understood.
Okay, Ayush, there are some hands, I guess. Okay. So this is a crude algorithm. You see, there are disadvantages of this algorithm. This is very time consuming.
Actually,
yes.
Hello. Yeah, but
Yes,
also like when we say convert the LP into standard via canonical form, so I just want to ask, in this case, we are just considering AX less than equal to B, right? Case, or AX equal to B.
Yes.
So if it is greater than equal to, then this crude way won't work for us.
It will work. It will work. That is why we had a slide over here which said that any LP can be converted into canonical form.
Okay.
By the way, this is not very important right now because you
Okay.
can skip this step later. But this is not a very specific to a problem. It is for general LPs. Okay. So you see, this algorithm, what it is doing, it is trying to find all possible basic feasible solution. In graphical method also we do that. We find all corner points, we obtain the objective function value at all the corner points and declare that corner point which having the highest or the lowest depending upon minimization or maximization as the optimum, right? So this is actually the same thing in an abstract way. You don't need to have two variables or three variables or five variables or n variables. It works for n variables. So this is same as the graphical method. We are obtaining all corner points. Over here, we are not labeling it as corner points. We are labeling it as basic feasible solution or extreme points. So this algorithm is same as the graphical method, where we are identifying the corner points. Over here, we are identifying the basic feasible solution, checking at all those solutions and giving the solution with the best objective function value as optimal. There are two drawbacks to this algorithm. First of all, it is time consuming. And the second drawback, which is more important, more worse than this drawback, is that it cannot detect unbounded optimal solution. You see, there is no way to identify an unbounded optimal solution or unbounded, yeah, optimal solution. You cannot identify unbounded optimal solution using this framework. Okay. So what we will do now is we will refine this framework. When we refine this framework, then we will try to find out ways of identifying unbounded optimal solutions as well. Okay. And by the way, this algorithm can identify infeasible solution. How will it be able to identify infeasible solution?
If
How
Some
will it
will
be able
have
to
negative values.
negative value.
it will not have any basic feasible solution. All the solutions will be basic solution, but it won't be basic feasible solution. Therefore, it is an infeasible solution, infeasible LP. Is that all right? Is that all right?
Yes, yes.
Yes.
Okay. Okay. So, yeah. By the way, these page numbers are huge, but at last time I have steps which are not very lengthy, so don't worry about the number of pages. Okay. So we will refine this crude algorithm. So what will we do? We will this framework I have given. We will the simplex work on this framework. What is the framework? Identify a basic feasible solution. Don't identify all. Just first identify one basic feasible solution, which is known as the starting basic feasible solution. Okay. Identify one basic feasible solution. I don't know how will you do, but you have to have starting basic feasible solution. If you don't have, you will not be able to initiate simplex. So you will have to have a starting basic feasible solution. If this basic feasible solution cannot be identified, then declare the LP to be infeasible. So if you're not able to find at least one basic feasible solution, then declare the LP to be infeasible and stop. Okay. Otherwise, proceed. What you will do? Check if the current basic feasible solution is optimal or not. So you see, in simplex, there is a way to check if that basic feasible solution is optimal or not. You don't have to see all the solutions, all the basic feasible solution before you can say if the solution is optimal or not. There is some way built in simplex which can identify optimal solutions given a solution, given a basic feasible solution. So there is a check. You are given a basic feasible solution. There is a check to see if that basic feasible solution is optimal or not. Do that check. If the solution is optimal, declare that solution to be optimal, and then you stop because you have found the optimal solution. You don't have to go further. If that basic feasible solution is not optimal, then identify new and better basic feasible solution. Identify new and better basic feasible solution, and resume from step 2. Okay. So this new and better has been written in inverted commas. Why? Because new doesn't mean anything and better doesn't mean anything. Just for writing there, we have written new and better. We have to define what new is. We have to define what better is. But for the time being, we will identify a new and a better. So you see, we are going from one point to the other, but we are always trying to go to a better feasible solution, basic feasible solution. We are not going towards any basic feasible solution. We are trying to go from one basic feasible solution to another which is better. Okay, so it is in a way trying to improve the objective function value and resume from step 2. If no other basic feasible solution is better, so there is also a way to identify that there is no other basic feasible solution which is better, then declared that LP to have no optimal solution, that is, it is unbounded. Then declare that LP to be unbounded and stop. So you see, this is not actually technically sound. This is just a framework. So we are saying we will work like this. I have not told you how to identify a basic feasible solution, how to do the optimality check, how to identify a new basic feasible solution, how to identify a better basic feasible solution. I'm not telling you anything. I'm just saying this is the framework we'll work with. This is how the simplex will work with. Okay. So there are, unlike the crude algorithm, the above algorithm need not search through all solutions, need not search through all basic solutions, and therefore it is faster. The point that it doesn't have to search for all basic feasible solutions or basic solutions makes it faster, and it can also detect unbounded optimal solutions. However, there are some questions, details are missing. How do we identify a starting basic feasible solution? How do we check if a basic feasible solution is optimal or not? How do we identify a new and better basic feasible solution? And related to question number 1, if our method fails to identify a basic feasible solution, how are we sure that there is no feasible solution? You see, in step 1, we are saying that if you don't identify a basic feasible solution, declare it to be infeasible. How are we sure that this failure of this step means no feasible solution? There can be another conclusion as well. How are we sure that if we are not able to identify a basic feasible solution, how are we sure that the conclusion is no optimal solution? Another related question is to question part C is, if our method fails to identify a new and better feasible solution, how are we sure that the solution is unbounded? We are declaring it to be unbounded, but how are we sure that the solution is unbounded? These are questions to think about. And in this lecture, I will not be able to give the answers to all of these because it is very time consuming to go through the algorithm, and in this amount of time, I'll not be able to do it. Therefore, what I have decided is to go with an example. So we will go with this example. It will not take a lot of time, 15-20 minutes. I will complete this example. We will see these steps. We will first identify, we will go through these steps, by the way. We will identify a basic feasible solution. We will identify a basic feasible solution. We will check if this basic feasible solution is optimal or not. If not, then we will identify a new and better basic feasible solution, and then we will proceed. So we will follow these steps. I'll not be able to answer these questions. I have just written it here such that you think about it, and if you are curious, then we can have, I don't know how will we how will I be able to cover this part. Okay. So my lecture, actually the theory has ended. We will just see an example. Any questions? Or did I not make any sense? It all went up your head. All right. Okay, so this is a problem of 3 variables. So you'll not be able to use graphical method to solve this problem. Okay. So maximize this subject to these constraints. So what we will do is we will introduce black variable first. So we will convert it into standard form. By the way, just give me a minute. I'll drink some water. Okay, so we have converted the LP into standard form. We have slack variables, and we are good to go. All right. So what we'll do is we will start with a basic feasible solution. So there are again theory over here. I will not go into the theory, but what it says is that when you are introducing slack variables and you are coming via canonical form and then standard form, you will observe, and one more thing, the right hand side is positive. So all those things are there for this example. Okay. So what you will observe is these slack variables can become basic solutions, basic variables. So x1 you can take at 48, s2 you can take as 20, S3 you can take as 8, and S4 you can take as 5. When you do so, you will observe that this this so this will be A4. This column vector, this column vector, this column vector, and this column vector are linearly independent. You will observe that A4, A5, A6, and A7 are linearly independent. Therefore, this is a basic solution. Now again you observe that these are positive, therefore this is a basic feasible solution. Basic feasible solution. So we have identified a basic feasible solution to start with. Okay, so first step is done. We have identified a basic feasible solution to start with. Is that clear? By the way, if you know simplex, you know this is how we do. So I will just reiterate simplex in a very different way. This is a very different take on simplex, but it is doing exactly the same thing. Okay. So we know the basic variables are S1 is equals to 48, S2 is equals to 20, S3 is equals to 8, and S4 is equals to 50. Now I am not using the simplex Tableau, which you are used to. I am writing it in an equation form. So what I have done is I have written the objective function value as Z is equals to the objective function value. Okay. Now you see, you can take everything on the left hand side. So I have just done that. Z minus 60x1 minus 30x2 and so on and so forth is equals to 0. And Ayush, your hand is up. If you don't have any doubt, you can put down your hand. Okay. And the other constraints, I have written it as it is. 8x1 plus 6x2 and so on and so forth is equals to 8. So I have just written that equations in a tabular format. Okay. Now the initial basic feasible solution is this. Now what we will do is we will go back to the steps. We have identified a basic feasible solution. Now we can proceed to step 2. It says that check if this basic feasible solution is optimal or not. I have not mentioned you what the step is, but for this example, you can observe that this is the equation row 0. When you write row 0 as Z is equals to 60x1 plus 30x2 plus 20x3, you see increasing x1 or x2 or x3 increases the objective function value. Currently, the objective function value is 0 because x1, x2, and x3 are 0. So currently, the objective function value is 0. Now, writing like this, you can see if you increase either x1 or x2 or x3, the objective function value will increase. So you can pick any of those. Either you can pick x1 or x2 or x3. But in general, it has been seen that picking the highest multiplier one result in quicker execution. But this is not proved. It is not proved that you have to pick the highest one. You can pick any one. But it has been a general observation that you should pick the highest multiplier one. Okay, so highest coefficient one. So over here we will pick x1, and why are we picking it? Just a minute. We will pick x1 and we'll make it positive, because when x1 becomes positive, the objective function value will increase. Currently it is 0. So we will try to make x1 positive. Okay, so this is the idea. Yes.
So is it an incomplete theorem or something like that?
Sorry, which theorem is incomplete?
Generally seen as in it is not proven, you're saying, right?
Okay. Okay, this portion. Okay, there is no theorem. Nobody has able to prove it, but it is observed that picking the highest one converges the simplex quickly. Not quickly, faster. Okay. Okay. So what I was saying is, so we will pick x1. What do I mean when I say pick x1? It means that we will try to increase the value of x1. Currently it is 0. If you increase the value of x1, you see the objective function value increases. So intuitively, each unit increase in x1 raises z by 60. So we want x1 to be as large as possible. So if the constraint satisfies, we can go x1 as infinity. Then our objective function will be infinity. But the constraint will not satisfy. Increasing x1 has effects on other current basic variables. You see, currently my row 1 is actually 8x1 and this is 0. Actually x1 is also 0, but for the time being I'm writing 8x1. This is also 0 plus s1 is equals to 48. We want to make x1 positive. That is why I have written 8x1 plus s1 is equals to 48. So x1, s1, since it is a variable in LP, it is greater than equals to 0. Okay, all variables are greater than equals to 0. So s1 is equals to 48 minus 8x1. Now you see s1 is greater than equals to 0, which implies 48 minus 8x1 greater than equals to 0. This should happen. So if you increase x1, it shouldn't violate this constraint. So how much you can increase x1 to? So you can have x1, sorry, not greater than equals to, it will be less than equals to, it will be less than equals to 48 by 8, which is actually x1 is less than equals to 6. So for this equation to hold, for this equation to hold, sorry, for this equation to hold, x1 should be less than equals to 6. So you can increase x1 up to 6. If x1 increases beyond 6, s1 will become negative, which you don't want to do. Is that all right? Is that all right? Please speak
Yes,
up.
sir.
I am out of time. Okay.
Yes,
Not
yes,
sir, you
yes,
can
sir.
call me Shubham. Okay. Okay. So we have done for the first equation. For the second equation, it is 4x1 plus s2 equals to 20. So 20 minus 4x1 should be greater than equals to 0, or x1 should be less than 20 by 4, which is 5. Have I done correctly? I think so,
Right.
I have done correctly. Okay. And similarly, for the third equation, you can do. So for the first equation, x1 is less than equals to 6. For the second equation, it is less than equals to 5. And for the third equation, x1 is less than equals to 4. Now you see x1 should satisfy all these values. It should be less than 6, less than equals to 6, less than equals to 5, and less than equals to 4. And for the fourth constraint, you see there is no x1. So it means x1 can take any value. It will not violate constraint 4. It doesn't matter what x1 take, because the coefficient x1 is not here. X1 can take any value. Constraint 4 will not be violated. So we are dividing. So we have 6, 5, and 4. We should take the minimum, because if we take 6, it will violate this constraint and this constraint. If we take 5, it will violate this constraint. So we take the minimum of 6, 5, 4, infinity. Why infinity? Because in row 4x, one can take any value. So we take 4. We can increase x1 to at max 4. We cannot go beyond 4. Okay, is that all right? Is that all right?
Yes, yes, sir.
Yes.
Now you see, if you make x1 4, x3 becomes 0 from this equation. 8 minus 2 into 4, which is 0. So x3 becomes 0. Is it all right?
Yes.
Yes.
Now you see what we have done. x1 is the entering variable. So if you are recalling simplex, we have an entering variable and an exiting variable. So x1 is the entering variable. We are entering x1 into the basis. x1 becomes the basic variable now, and x3 is the leaving variable. Is it all right?
Yes.
x1 is the entering variable and s3 is the leaving variable. Now the new basis is, so this is not the new basis. Now the new basis is s1, s2, x1, s4. This is the new basis. s3 has left the basis. Okay. All right. So this was the table. So this was the original table. Now when x1 has become the basis, you see, whenever you have a basic variable, you make that coefficient 1 and other as 0. This is what we do, right? This was the original table, by the way, the first table. So you make that 1 and make other as 0. That is what we do, right? Is that clear? Over here also we will do the same. In this row, we will make this coefficient as 1. How will we do? We will divide this row by half. We will divide this row by half. So by 2, by 2, by 2, by 2, by 2. Is that all right? Is it all right?
Yes,
Yes.
Right? And we will make others as 0. How will we do that? So by doing this, we have this new row as x1 plus 0.75 x2 and dot 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 something we have. So this new row has 1 times x1. You just do elementary row operations, which you have done in matrices. What you do is you do row 1 becomes row, so row 1 dash becomes row 1 plus, not plus, minus 8 times row 3 or row 3 dash. So I will write it clearly. So first step we have done is row 3 dashed becomes row 3 times half. This is the first we have done. Now row 1 we will do row 1 dash becomes row 1 minus 8 times row 3 dashed. Row 2 dashed will become row 2 minus 4 times row 3 dashed. And row 4 is actually 0. It becomes row 4 dashed becomes row 4. So these are the elementary row operations we will do. Is it all right?
Yes.
And for row 0, we will also do row 0 dashed will become row 0 plus 60 times row 3. Okay, so we'll do it for all the rows. Is it all right?
Okay, yes.
Okay, so this is what I have written over here. This is the new table. This is the new table, and you observe all the rows have changed. And now Z is taking value 240. And if you don't believe that this is correct, you can just check in the objective function value. You see the objective was 60 times x1 and x1 is taking value 4. So 60 times 4, which is 240. So this value is actually the objective function value. This value is the objective function value. And now for the first row, S1 is the basic variable taking value 16. S2 is the basic variable taking value 4. X1 is the basic variable taking value 4. And S4 is the basic variable taking value 5. Now again, so you see what we have done. If we go back to the steps, we checked if it is optimal or not. We saw this is suboptimal. Why? Because we could improve the objective function value. So this was not optimal. We identified a new and better basic feasible solution. What is the new basic feasible solution? This is the new basic, sorry. This is the new basic variables, and this is the new basic feasible solution. This is a new solution, new basic feasible solution, and it is better. You see the objective function value from 0 to 240. It is not only new, but it is also better. Now we will repeat. What will we do? We will see if this solution is optimal or not. How will we do that? We just write the objective function now. Z is equals to 240 minus 15x2 plus 5x3 minus 30x3. Okay, I'm just writing from here. Now you see, if you increase x2, your objective function value will decrease. If you increase s3 also, your objective function value will decrease. But if you increase s3, your objective function value will increase again.
Plus.
Sorry?
Sorry,
Okay.
nothing.
Okay, so x3 will become the new entering variable. So what we will do, we will check again. So this is what I have written over here, everything. We will check again for the 4 equations. We will check again what should be the appropriate value of x3. How much can we improve such that no other variable becomes negative. Okay. So for all these, we will check again. And we will take the minimum test. So this is known as the minimum ratio test in Simplex Tableau. You take the theta, you take b by whatever is that. So if you go through that Tableau, you will do the same thing. We are doing the same thing over here also. This Tableau is same as the Simplex Tableau which you write, but we are doing it using equations. And if you remember, for optimality over there, we check Cj minus Zj, or somebody can also say Zj minus Cj. You check these values. So these Zj minus Cj are actually these values, 15, minus 5, 30, and so on and so forth. We are actually doing the same thing. The Tableau, we are doing it here using equations. So if you remember, for maximization problem, if your Zj minus Cj or Cj minus Zj, I don't remember. I guess it is Zj minus Cj. If it is negative, then that variable becomes the entering variable. So over here also we are saying that x3 is the entering variable. And we can see using the equation x3 is the entering variable. And then we do the minimum ratio test. So that is what we are doing over here. We are doing the minimum ratio test. And we are observing the maximum value of x3 can be 8. And x3 is the entering variable and s2 is the leaving variable. So again, this is the second Tableau. So this tableau and this tableau is the same. I have written over here just to illustrate that since S3 is the entering variable and which row it has entered, it has entered using row 2. It has entered using row 2. So in row 2, you make this as 1. How will you make? Over here, you multiply it by minus 0.5. Sorry, minus 2. You multiply it by minus 2, the whole row. This will become 1 and then make the others as 0. Just do the same elementary row operations which I have written over here. And then you will obtain this new tableau. Okay, you see x3 is the basic variable over here, and the basic variables are s1, x3, s1, x1, and s4. This is the new table. And now if you observe, z is equals to 280 minus 5x2 minus 10s2 minus 10s3. No other variable, if increased, can increase the objective function value. Therefore, this is the optimal tableau. And the solution to this linear programming problem is this: 24, 8, 2, and 5. Okay. And the solution is optimal. I have completed this portion and I have left a proof of LP feasible region is convex. If you have time, you can come and read. I have taken 9 minutes extra, I'm sorry, but I wanted to complete all portions. Okay, so coming back again over here, what we did is we identified a basic feasible solution. We checked if that basic, by the way, if we couldn't identify a basic feasible solution, we declare it to be infeasible. I have not told you how it is infeasible, why it is infeasible, how are we checking it is infeasible or not, because of we don't have time. We identify a basic feasible solution. We checked if the current solution is current basic feasible solution is optimal or not. If it is not optimal, then we find a new and better BFS. And then we repeat the step. We check again. If not, then we find a new and better BFS. And if we find that it is optimal, we declare that BFS to be optimal. Is that all right? Is that all right? Thank you. So these are my details: website, LinkedIn, and email. I would request you to send some connections in LinkedIn. I would be very glad to have you as my connection. Any questions or doubts? Yes.
No. Thank you, Shubham.
Okay. Thank you so much. So
Thanks,
I hope I
Shubham.
didn't make.
We will
I hope
see.
I
Yeah,
didn't make this too complex. Yes, go on. Yes, go on.
Hello. Yeah. So I just it was a wonderful explanation. I liked it, your way of explanation, and I've actually understood what is convex hull. So that was actually I was trying to get this definition, but the way real I get to know. My other thing is in undergraduate days we studied about the Bigam method and two-phase method. So is it the same thing can be applied there, or like some changes can be happened?
No. So the theories which we have built here, we have not talked about a lot of theories, but these concepts you can take and you can use it in the Bigam method. No, just you can translate these ideas and do the Bigam method as well.
Okay, no. And I want to ask one thing, we gone through like this Simplex and everything. So this Simplex algorithm is also used in Simplex, or some different algorithm is used in Simplex?
No, Simplex algorithm is used in Simplex. Sorry, Simplex. When solving LP, Simplex algorithm is used in Simplex.
Okay. There is no other algorithm than Simplex which is being used.
No, but there are algorithms to solve LP apart from Simplex. One is known as interior point method.
Okay. Okay. And others are like interior point apart from interior point?
I don't currently know. There are other professors here who can add to this, but I know of two methods of solving LP. Any more doubts?
So we will be meeting in Mumbai?
I will come there on Tuesday, yes.
Okay, so great.
Thank you. So I guess we can end this session. Do connect with me on LinkedIn. Okay. Thank you so much.
Thank you.
Thank you, Shubham, for the session.
Thank
So
you,
I leave
Shubham.
the session. Thank you so much.